than Earth is, and so therefore it takes close to 2 years, Earth years, to go around, about half the diameter of Earth. A day is right about the same, so it has a similar axial tilt and similar rotation. Smaller planet, so you're ending up with about 1/3 the gravity. It's a cold place today, at least. Your average global surface temperature there is well below freezing, and combined with a very, very thin atmosphere, you end up with not a lot of liquid water around today. But we think in the past there was definitely, it looked a lot more Earth-like than it does at modern times. And feel free to pipe in, ask questions if you have them as we go. I'll do my best to answer. But so the relationship, why Mars, and what's NASA's ambitions? So the Mars exploration program, it's an official program within NASA that's different than other solar system bodies that where we'll just send one mission to Venus to learn something, and maybe 30 years later send another mission to Venus. But Mars has a architecture within its mission scheme. So these are these missions build on each other, enable and enhance future missions, and there's a mix of types. So it's some are competed. So the next mission going to Mars is being led by LASP and my boss. It's the MAVEN mission going this fall. So that was he wrote a proposal that won the mission to Mars, and then other ones are developed by NASA centers and keeping them in business, I guess. And out of NASA's about 20 billion a year. Well, now it's down to like 16 or something, and after Friday it's probably down to 14. But whatever. So about a quarter of planetary science, which is about $1 billion a year, goes to studying Mars, and so 250 million a year goes toward the Mars program. And then the other, besides planetary science, there's the astrophysics side, the Earth science that does a lot of the climate modeling and understanding climate change and modern weather, and then the heliophysics is sort of the Earth-Sun interactions and space weather and storms and things like that. So yeah, this one's working fine. I don't know if you want to just leave that here because you'll need it. Okay.
I'll come back in your class.
All right. So sort of the overall goal here at Mars, as I'll show you, it seems like there was a lot of water there in the past. So modern day don't really have this, but water seems like a cross-cutting theme to understand the geological history, understand the history of climate and the climate change. The possibility of life there seems to require water, at least from what we know about life on Earth. And then, of course, water is pretty heavy, and to send it all to Mars for when humans are there, we want to find in situ resources to use. So really sort of looking the where, the when, the form, and the amount through time through these cross-cutting themes. So what's happened? The early missions, I'll show you data, seemed like a pretty cold, dry, inhospitable world, but some sort of tantalizing clues of past water. So and then in the past 15 years or so, when NASA's spent a lot of resources and efforts heading to Mars, really a revolution in our understanding, and a rich geologic history. Seems to be water everywhere on Mars. We see these dried up river valley systems, evidence of deltas and past lakes, and then now the chemical signs of water from Mars are adding into this understanding. So it seems like a pretty good target if you're looking for life beyond Earth, which is part of NASA's mission to try to find, or at least survey, whether or not life developed anywhere else. So starting, a little over 100 years ago, well, certainly people knew Mars was different, right? Didn't move like the rest of the stars. It has retrograde motion, zigzags back and forth across the background of stars, depending on Earth and Mars's orbits. So once telescopes, became good or so, you get a view like this of Mars, and with your artistic embellishments, you draw a map like this that has all these interconnected lines, which I'm sure you can see those there, but Italian astronomer Schiaparelli mapped the canali, which are channels. So he saw channels all over the surface of Mars. And the American astronomer, prominent American astronomer, developed the Lowell Observatory outside of Flagstaff there. He had the world's best telescope. And he agreed that, yes, there were canals, and not only that, they were built by intelligent Martians. And so his view, again, you can see the albedo patches here, and somehow he saw these lines across Mars. And but this became the norm of the day. So this is a New York Times article, 1906. There is life on the planet Mars. Recognized the greatest authority on the subject, declares there can no doubt be that living beings inhabit our neighbor world based on this highly advanced system of canals. The argument was that Mars is farther from the sun, probably colder, and the water would be toward the poles. So these systems of canals were to pipe the water toward the equatorial regions. And he had noticed albedo changes during the year, and so that led him to think those are vegetation changes from their massive irrigation system across Mars there. And this is where the state of science was in 1906. And of course, this spurred on all sorts of good sci-fi movies, and with little green men running around, and H.G. Wells that had the world's book, The Martian Invasion. And of course, when that was broadcast, and right around the time of World War II here, people were kind of on edge, and people were panicking, jumping out of windows because the Martians were coming. And still, this is what the thought of the day was about Mars. So then we finally got to the modern era, and this was spurred on by the Cold War. So Russia launched Sputnik in 1957, ahead of our first satellite, and then at that point, President Kennedy, or shortly thereafter, President Kennedy said, "We will land people on the moon." So this initiated the space race, but it went well beyond the moon, and that's kind of a missed fact by a lot of people, that it was a race to get the first flyby of Venus, and the first thing to go by Mercury, and the first lander on Mars, and so it was beyond just the moon, and this led to the development of the first Mars program. So currently there's 5 spacecraft at Mars sending back data every single day. We have 3 orbiters there right now. Mars Odyssey got there in 2001, and I'll go into these in more detail. The European Space Agency, ESA, sent their own mission to Mars, Mars Express. The 2 rovers that went back in 2003 landed in 2004. Those are supposed to last 90 days, and one is still operating, sending back great data every day. 2005, we sent Mars Reconnaissance Orbiter, a very capable NASA mission, and then just this past August, we had the Mars Science Laboratory, a $2.5 billion mission to Mars. So this is about $500 million. This is $2.5 billion, and but it's working. Well, the computer went into safe mode over the weekend, some cosmic radiation event, but there's of course redundancy, so they're switching to the B computer and think it won't hamper science at all. And yeah, just to point out, getting to Mars or any other planet is not easy. So here's the mission name, the country that was doing it, and you can see the fight here between the 2 countries, and then launch in chronological order, what they were going to do, and then what happened. So Russia's first 5 attempts there did not reach Earth orbit, didn't reach Earth orbit, failed. So not until Mariner 4 did something actually succeed in flying by Mars. So this was probably $1 billion in modern day dollars, and it took 21 pictures of Mars. So but that was success. That's what it was meant to do. Another fail, and then more of the Mariner series 6 and 7 returned a few more pictures. Mariner 8 and 9 were identical copies of each other, and 8 blew up on the launch pad. No useful data, lander destroyed. It's a common theme. Some data, few photos, little data, and then Mariner 9 there did a great job. And then the 2 Vikings in the mid-1970s, just amazing missions. And in modern day dollars, that's probably $5 billion went into these 2 missions. So it's 2 orbiters and 2 landers, identical, and all 4 components worked, all 4 spacecraft. And then you know, we blew one up on the launch pad, lost that one just before arriving. Yeah, and then we had a climate orbiter. This was the notorious converting between English and metric units one that flew right by Mars because the engineers built it in English units, sent it to NASA. They assumed those were SI units. So pay attention to your units, they're important. $300 million important in that case. And then, yeah, currently we have a lot of these things going on at Mars. So I sort of wanted to give a historical, you know, historical look at Mars exploration from the US side, because, well, those were the more successful ones, and we have more data on those. But this Mariner series of spacecraft, this is part of the space race to explore the inner solar system. So Mariner went to Mercury, to Venus, and also to Mars. So it's sort of the evolution of them. And Mariner 4, like I said, was the first success at Mars after about a dozen failures between the 2 countries. Mariner 6 and 7 also flew by, collected a lot of good pictures, but they missed the large volcanoes and, you know, the canyon that's as long as the United States. They didn't see just by the flyby geometry. And then 8 and 9 were identical spacecraft. 8 blew up during launch. And you know, rocket technology was just coming along there. So even if you had a good spacecraft, not necessarily are you going to get to Mars. And then Mariner 9 was really the first good mission to Mars where there's a lot of useful science data. And it was the first satellite put in orbit around another planet. So this was a race that US won in this case. But it got there, it was a global dust storm. So if it had just been a flyby, it had taken pictures of a dusty atmosphere and you know, the disk of Mars, and that's all you would have seen. So it lasted a couple months before the sky started to clear. Fortunately, the spacecraft lasted that long and was able to actually take images of the surface and revealed the volcanoes, the large canyon system, and then these intriguing signs of water on the ancient terrains. So of the imagers for Mariner, there's a lot of text on here. I'm not going to read it all, but television camera on a scan platform, and you know, using a Cassegrain telescope, had a red and a green filters, coupled to different exposure times, and then a slow scan Vidicon tube, which put the optical image into electrical signal, compressed heavily because the data rate back and forth is certainly not very good at this time, still isn't, and then send it back to Earth. And last built the ultraviolet spectrometer on this, also had an infrared, but for the visible cameras, this is what they had, and lasted almost a year, and sent over 7,000 pictures back of the surface of Mars at varying resolutions. But did cover the whole planet, and you know, way surpassed all previous missions to date. So here's some of the shots from Mariner. From again, this is, you know, 1960s technology. It's amazing that we have any data, but this is the global dust storm. This is the dust in the atmosphere. Here it's clear. You can see some craters, but this is sort of the state of the field at the time. The dust storm clears, and you can see the volcanoes. These are actually poked up through the dust storm. So these 3 large volcanoes first revealed that. So it's really showing, you know, Mars is thought to be like the Moon or Mercury, and not a lot of activity. But once Mariner 9 got there, showed a very different view of the surface. We knew there were polar caps, so we could see those from telescopes. But first, detailed mapping of the ice sheets at the poles of Mars. There's the North Polar Cap. And Valles Marineris, which was named for the spacecraft that discovered it, this enormous canyon system. And you know, on Earth, the canyons are formed by running water. This is from tectonics. This is the crust stretching top to bottom in this image, and it's really just ripping apart. And the canyon runs the length of the United States. It's 10 kilometers relief from here down to there. So this is a huge feature on the surface of Mars. Yeah, question?
So how do you know that it's plate tectonics instead of water?
Well, we can map faults all along the bases of these, and in places we see the crustal block here drop downward. So we can put together pretty pretty clearly that this, and water later on probably flowed within this canyon, but it didn't carve the canyon. Like the Grand Canyon is a sinuous canyon, very narrow, cut down deep, whereas this is a very linear feature, and we see the faults along it. And then the big volcanoes are just off the side here. So it's all that magma that was coming up to build those big volcanoes, pushing the crust up, and you'll get radial stresses there and rip open the crust. And some higher resolution, seeing sand dunes, so recent wind-driven activity within a crater here on Mars. So, and then the big story was the evidence of past water. And so these are some of the better shots of, what appears to be a dendritic branching system that all combine downslope into larger chunk segments. Same thing up there. So these look like dried up river systems. There could be another fluid that carved these features. Liquid CO2 has been proposed, but it doesn't really work out given the thermodynamics at Mars. But so we're pretty confident this is flowing water, and we know there used to be a lot of water at Mars given the D to H isotope ratios. And then some places you can see very large-scale flood features. So you have these two classes, the river valleys, and then large-scale floods that, again, were first identified by Mariner. And still we cannot see these from Earth. So yeah, like I said, this is it really sort of changed people's views of Mars, and most of these missions did actually. So first, just an old cratered, geologically dead surface that never had much activity, but Mariner showed otherwise, that at one time there must have been a thicker climate that could support liquid water at the surface of Mars. There were complex geology there, lots of volcanism, lots of tectonics, the bombardment history, and then the flowing water. And then this really spurred on, okay, well, what can we do next? Let's send these Viking missions to Mars. So that was the next step in the process. So the Vikings went in the mid-70s, first time to actually land a spacecraft on another planet, and did it twice with two different landers. So both two identical systems, an orbiter and a lander, that reached Mars. They took pictures to map out where a safe landing site would be, and then a couple months later released the landers, and they both landed, soft landed on the surface. And the orbiter's pretty good resolution, and it wasn't a perfectly elliptical orbit. It was closer to the planet in some places, farther away in others. So you get sort of a range of resolutions there, but seeing things pretty good. And also on the ground had meteorology, so what are the winds at the surface of Mars, what's the atmospheric pressure, and they had these life detection experiments which were designed to look for signs of life. And by this point, figured no little green men, but maybe microbial life could have arisen on Mars. And those did show chemical activity, but really no conclusive signs of life came out of those. And also just a very harsh surface environment. It's basically like coated in hydrogen peroxide, which not so good for biology and preserving organics a long time. And first atmosphere profiles from those things. But the orbiters, this is the best picture I could find, but a red and a blue channel. So Mars is red, so the red gives us a lot more information than the blue generally. So Cassegrain telescopes here, and with a number of different filters here, looking through the visible for the most part, and again TV relay back to Earth there. Also infrared radiometer that gave us some thermal infrared data, and a water detector in the atmosphere that was looking at isotope ratios. So from Viking, compared to that Hubble image on the title slide, we have very good mosaic, sort of at 250 meter per pixel resolution and color for the first time from Mars. And it's not true color, right? It's a red filter and a blue filter, and then you fake a green filter and put them together and you get this. And the colors aren't quite right, we've learned. This is a little redder. It's more of sort of a mustard yellow almost than the red that you see here. But first good views of Mars, and I mean, when I was doing my PhD, it was mostly based on Viking data. I was using the images and piecing them together in mosaics and doing mapping of Mars. But even more evidence of water on Mars. So better views of these river valley systems that really look like precipitation, surface runoff, and incision into the crust. And then smaller features here. And then some of these huge flood deposits that are stretching across Mars here. So, I mean, some of these are hundreds of kilometers across, and this is a floodplain. You can see these streamlined islands of where this entire thing was filled with water that was flowing off to the north. So enormous floods came out of Mars's crust in the past. And then good views of the volcano, so starting to understand sort of the heat history of Mars and heat release from Mars. Large landslide deposits that have come off. Multiple craters up here at the top, indicating multiple eruptions across time. Yeah?
The ring around that image, is that a band of cliffs, or is that something?
Yeah, these are all cliffs here. And again, some of these are 10 kilometers high. And then, so here's a big cliff here, and then you can see this little bait deposit. So we think these are huge landslides. These are landslide scars of the whole piece of the volcano just sloughed off at some point. And then off that side, there's even more landslide deposits.
So what's the rough dimension?
Oh, Colorado would fit underneath this one volcano. And it's 2.5 times the height of Everest. So this is a big volcano, 78,000 feet high or something like that. The slopes are only about 5 degrees, so it wouldn't be a very exciting hike up it. You'd hardly know you're going uphill. But yeah, except for here. And then there's some good rock climbing to be had, with only 1/3 the gravity, so it helps you out there. You can be Superman. And of course, the 2 landers also gave us the first shots of the surface. So we didn't know what the surface of Mars looked like. See sort of like a desert Southwest type of a view. Lots of rocks, sand blowing around, frost. These are at fairly high latitudes, so you'd get frost in the winter time. But measuring daily meteorology of these sites. Here's a few more shots of the surface, some sand dunes. Here's some of the frost there. So again, our first looks at the surface of Mars.
Yeah, as I said, like how dry is the atmosphere there? Is that frost coming from just
Yeah, this is CO2 frost. Yeah, good question. Yep. So you'll get dry ice frost down to about 40 degrees latitude during the winter season in that hemisphere at Mars. So we can see this progress and then retreat through time. So yeah, since the atmosphere is, there is water in the ice caps, but also dry ice too. So you get those 2 phases together. So Viking, over 100,000 images. So we went from 20 to 1,000 to 7,000. Now we're over 100,000 of the surface of Mars and complete mapping. So really, again, a new jump in understanding of how complex Mars is and how unlike the moon it is. And these light detection experiments I won't really discuss, but some sort of gave a positive sign, but then when they ran the control, they also gave a positive sign. So these, and they really weren't looking for the right types of things. It's just not long after DNA had been discovered, they were building these experiments. So, looking back, we could do a lot better now. And then after Viking, it was done. Nothing went to Mars till the mid-90s. And, we had recession, we had beat the Russians, the Cold War was over, no motivation, I guess, to go back. And we had a lot of data to look at. So nothing went to Mars for 20 years from any country until the mid-90s. We finally started sending things back to Mars. And this was a lander, the first rover, first thing to drive across another planet's surface. This one went about 50 meters total. So not like we're going big distances here saying, well, it is setting a driving record, but since there was none, no baseline. But really, there's some very modest science instruments on board, a chemistry instrument, a small camera, but it was really engineers doing what they do best, figuring out how to drive on another planet, the JPL guys there. but it did really spur interest. You know, the public, this cute little rover driving around on Mars was really piqued interest, and is about the size of a laser printer, this one. So pretty small, not a lot of mass, and but it did show us you know, another spot on the surface, and it had a stereo imaging system on the lander, and not on the rover though. So yeah, so a few filters to sort of give us the view. So again, here's from the lander, taking the picture out, the tracks of the rover heading, drove up to the rock, put its instruments on it, studied the chemistry. These are all like just run-of-the-mill volcanic rocks. Nothing very interesting here. Yeah, well, there's interesting stuff, meteorology, and see how sand is blowing around. But if you're trying to answer the question of water, this was not the best landing site to go to. But it was a big, flat plain, and that's where you want to land, especially if you're an engineer, right? The scientists, we want to land like in the Flatirons and understand that geology, but the engineers want to land in Kansas. And so we have every mission we have a fight of where we can go to get good science that's not just going to be a parking lot, and but where we can also land safely, because if you don't land safely, you know, you're not going to get any science. So there's a lot of battles that go on. And then we started sending a slew of orbiters, and starting with Mars Global Surveyor. This was a copy of an earlier version that blew up on the launch pad, and so they had copies of the instruments, built it again. That rocket worked, and lasted a decade, Earth decade. Yes, this was testing a new braking technology. So, right, you're traveling very fast on the way to Mars. I don't know, tens of thousands of miles an hour, and you have to slow down and get into orbit. So instead of taking a bunch of fuel and firing retro rockets forward to slow your motion, this had an aerobraking technology where it put out flaps, it skimmed through the atmosphere. There's enough drag there, it slowed it down. So it took 6 months to, you know, go from. So you're coming in and you're skimming the atmosphere, and then you get a little closer and you slowly beat this down until you're into a polar orbit around Mars. So that process took 6 months, but you didn't have to send the fuel and thus raise the cost of the mission by 50 million and have a heavier lift rocket to fly this thing. So it got there. We had to wait a while before there was any good science that came out of it, but it worked. And yeah, if these didn't deploy, you know, we'd have been in trouble. But they worked. And basically, 3 instruments on this, 3 main instruments. A thermal emission spectrometer, so this is looking in the thermal wavelengths of the infrared. A nice camera sent along, and then a laser altimeter. So this was bouncing laser pulses off the surface of Mars as it was in orbit around Mars. So at 10 hertz frequency. So as the planet turned underneath it, and you continue bouncing laser pulses, you know, you can figure out the range between the spacecraft and the surface by the travel time, and then from that figure out the topography. So I'll talk most about the camera, but I'll mention one slide on each of these, I guess, too. So this camera, the Mach Mars Orbiter camera, it was 3 different cameras. A narrow angle one that was looking at high resolution of the surface. So now we're down to sort of meter scale or a few meter scale imaging of the surface of Mars. And so it imaged about 3% of the planet over its decade lifetime. Right, if you're zooming way in, then you're not going to cover the whole planet. So there's trade-offs there. And then had a red and blue wide-angle cameras that were repeatedly imaging the planet, and then looking at daily weather patterns and changes in the atmosphere. And over its mission, sent back almost 250,000 images of the surface of Mars. And then the altimeter was this laser that was bouncing the pulses, and then TESS was the Michelson interferometer broadband, looking mainly in the thermal infrared, telling us something about the surface. So from the thermal data, we can derive something like this: thermal inertia, the resistance to change temperature of the surface. So we can look at thermal emissions during the daytime and then again at nighttime and see that contrast. And you know, a rock's going to heat up slowly in the morning, but then once the sun goes down, the rock's still warm, whereas, you know, sand or dust will heat up very rapidly in the daytime, but then as soon as the sun's down, it'll lose that. So this is probing the bulk density and thermal conductivity of the materials at the surface of Mars. So where this is blue are very dusty regions. Where it's red, there's a lot more rocks and a lot of bedrock. So new types of data from Mars, but again, sort of at fairly coarse resolution.
Just like a patch of the Martian surface, or is like a map of the entire planet, or what are we looking at?
Oh yeah, this is the whole planet. So here's the canyon system, Valles Marineris.
Okay.
And then some of the flood deposits, the volcanoes, you can sort of see them here. There's Olympus Mons. Those scarps are showing up as more rocky than the surroundings. But yeah, so we're looking globally here. And here's an impact crater on Mars. That's the size of the US. So, and then these are the individual orbit tracks of the spacecraft through the repeated observations. So you measure in the afternoon and in the middle of the night and look at those temperature contrasts and apply your thermal models and figure out you know, thermal properties of the surface of Mars. And so, you know, when we're doing lander planning, we don't want to land in dusty regions. Well, one, everything's covered in dust, but two, the rover will get stuck. And we think some of these blue regions, there might be 10 meters of dust, just fine grained dust sitting there on the surface. So those are immediately out when we're doing landing site selection activities. And then the altimeter with the laser, here's what we knew about the topography before it went. These are 1 kilometer contours, so it's a contour map. And that, you know, and again, when you're trying to land things on the surface, this is fairly coarse. So we went from this view, in 1 year of data, we ended up with this view of Mars. So just a revolutionary change in our understanding from this laser altimeter. One went to the moon recently and now has better maps than for Mars. But you know, really revealing the details of, you know, sort of the morphology of the volcanoes, canyon systems, more volcanoes, the big impact craters, more volcanoes, these flood deposits coming out here, and trying to understand sort of the surface, the thickness of the ice caps, the amount of mass that's there in terms of water and CO2. So learned a heck of a lot, and now some of these estimates of Mars were off by up to 6 kilometers vertically. So imagine trying to land the lander there and surface is 6 kilometers higher than you thought it was going to be. Not a good situation. And then from the imager and combined with the topographic information, so from Viking we saw some river valleys, and here's just a random Viking shot I pulled with the river valley there and a stubby little tributary. So I went back and was looking at some of these same areas. So these are the same 2 impact craters that are in this one. So instead of you know, there just being one fairly immature drainage network there, it's this dense network of river valleys, and you see this all over the planet Mars. So whereas this could have formed maybe just by groundwater, you know, seeping out of the ground and slowly carving a channel, this is much more indicative of precipitation and surface runoff. So really requires an adequate climate to do that. Maybe a couple bars worth of CO2 atmosphere to make water stable there at Mars. Just another shot of what had been seen before versus what we now know is there. So I do a lot of hydrology work at Mars. And then also deltas, right? If you have a river flowing, then if it flows into a standing body of water, you should dump out that sediment as you slow down the velocity and form a delta. And we found over 50 of these now. Here's one of the best known ones. This is Eberswalde Delta. Similar in scale to Earth deltas, but now we can really start to understand where there was standing bodies of water on the surface of Mars, whether or not there were oceans there in the past, and reconstruct some of the hydrology. You know, what are the flow rates here, the discharge, the depths of these things. And then also related to water, discovered a new class of feature, these gullies here. So this is you know, high up here and then a cliff face and then a valley, and you can see all these different gullies that are coming out of the surface, and note the scale bar. These are pretty fine scale features, but they often have an alcove type head, channels coming down, and then an apron of debris down at the bottom of them. And some of these seem to cover up modern sand dunes. So it was thought that they're very recent features, that water seeping out from a particular layer along and at an aquifer there, occasionally bursts forth, flows down the surface, and then deposits the stuff at the bottom. So arguing for modern aquifers on Mars. And then with this camera, went back and imaged the same spots over time and saw new gullies form. So these top two are the same crater. Here's an old gully channel, and then here's a new, presumably water ice deposit that has formed between 2001 and 2005. And then the same thing here, you have a new gully deposit that comes out there, again, over the course of 6 years. So we think water occasionally is bursting forth and flowing out onto the surface of Mars even today.
How do you distinguish between that and landslides?
I'll show you some pictures of landslides. These generally are branching and sinuous, and then you'll get the large deposits at the bottom. And this alcove-shaped head is more characteristic of these compared to the landslides. But we have good images of landslides and dry landslides on Mars, and they do look very distinct. And these are bound to craters and at particular latitudes, for the most part, mid-latitudes. So it's some different process than just gravity-driven. So, and yeah, the face on Mars, remember this conspiracy theory? So Viking took this picture. You can see the difference in quality between Mach and Viking. 1976, you see this face on Mars, and of course, intelligent beings building their own Mount Rushmore there on Mars, and looking very human-like even. So, but we went back and imaged the same place, and it appears to be just an eroded mesa. So, you know, the answer is the Martians realized we were onto them, got out their bulldozers, and plowed this thing over before we got back there to take another picture of it. But yeah, so we kind of put that to rest, but of course the conspiracy theory people never will stop. So what do we get out of a Mars orbiter camera? Really this fine scale nature of water proved that there is past lakes and standing bodies of water, and then also these shallow aquifers. And so if you're looking for life beyond Earth, Mars is starting to look more attractive. So 4 years later, Mars Odyssey went, and don't have much on this. It had a thermal emission imaging spectrometer. So this is a multi-band spectrometer, and had visible capabilities at 18 meters per pixel, and then global infrared data at 100 meters per pixel. So again, sort of looking at these thermophysical properties of the surface, mapping out rocks versus dust, getting some composition information of the surface from that as well. And then the Europeans sent a mission in 2003, had a really nice camera on board, a radar, and a nice hyperspectral imager. So this was a stereo camera. So as it flew over, it took shots of the same spot with 10 different imaging systems, and from that they could reconstruct 3D geometry. So 10 meter resolution color stereo imaging of Mars. So here's now the summit craters of Olympus Mons, looking at that. And so we're making vast improvements and learning a lot more. Discovered evidence of ice deposits on Mars. These are dust-covered glaciers. Here's the oblique view over there. But the ice up here is flowing through this constriction, and you can even see crevasses and things along the side of that. So we're pretty confident these are ice deposits. And then we've sent 2 hyperspectral imagers. Omega was the first to get there. So we're looking at visible through near infrared here, through a bunch of spectral bands. And again, not a circular orbit, so you're getting a large variety of spatial resolution there. But this is kind of a crummy picture, but mapping out different minerals on the surface of Mars. So you can pull out of this data cube the spectra, again, from the visible out through the near infrared. So you have the surface of Mars, or the letters here. You compare them to your library samples that you've measured on the laboratory. And so these wavelengths are especially particular, or especially diagnostic of water and OH bands. So this OH bond shows up here a lot, so we can map out minerals with water in them, Also iron and oxygen bands show up very easily here. So we can start to actually see the chemistry and mineralogy of the surface of Mars. Map out the ice deposits at the poles, what's water ice, what's CO2 ice. Look at clay minerals, implying that a lot of water has percolated through this crust in the ancient past. So we're getting there. Reconnaissance Orbiter 2006. This was another NASA-run mission. Here it is being put into the fairings of the rocket there, getting ready for launch. Really good imager on this one, the high rise. So this is a visible imager and looking at very good resolution. Then another hyperspectral one as well. So the hyperspectral, fairly similar to the European one, a little better resolution, a little better spectral resolution, more bands, still looking in the visible near infrared, and a lot better spatial resolution. So mapping out the surface mineralogy of Mars. And from that, we can figure out where there's clays within the surface of Mars, again, implying lots of water there in the past. And then the imager, so here's a serious camera. This is a 1/2 meter primary on this one. So three color bands, sort of broadband, and then a bunch of CCDs behind it to give you very, very good images. And so you're getting 1/4 meter spatial resolution at the surface of Mars from 300 kilometers above the surface. And the lack of atmosphere really helps, right? So, but when you're playing with these images, they like start crashing Photoshop because even the compressed JPEGs are larger than its onboard memory. And here's a picture of Earth and the Moon from Mars with this imager. So this one actually can look at real change on the surface of Mars, fine scale change. So here's the Opportunity rover. You can see shadows of it, the tracks of the rover as it was driving around there. So this one's still going. Pretty cool to look at other missions. That's just a cool shot. So it's true color here. So here's some of the dry land slides, and you can see they do look distinct. These are sand dunes, and then these dark tracks are dust devils that go over the surface and churn up the dust and leave a lower albedo surface. So you can map out modern day meteorology. You can go back and image the same places, see new craters form. So this is a 10-meter crater that formed, and the blue there is water ice. So this is at high polar latitudes and hitting down into the permafrost regions of Mars. So you can look at the impact rate. Here's a landslide caught in action. So this is high, you're going down a cliff face, and that's the landslide. Just serendipitously happened to catch this, as you know, no one gave us the memo, but caught it anyway. They've seen a few of these. Oh, there's a dust devil and its shadow, so you can start to look at the height of dust devils and how quickly they're moving, meteorology. The polar caps, the CO2 ice, is sublimating away very rapidly. Mars might be in some rapid climate change of its own, and so you can trace the rate of CO2 loss over each annual cycle of these things. This is called Swiss cheese terrain. And not just the gullies, but here's through the summertime a series of images at this particular crater where you see these streaks develop and move down slope. So this is also thought to be water seeping out over the course of a few months and it only happens during the summertime. Seen this at a few different craters on Mars, but again arguing that you have shallow aquifers here in the subsurface. And then when the rover was going in last August, they thought they'd try to capture it, and they got it. So here's the parachute and the lander there on the way down to the surface of Mars. And then if you go back and fly over and take an off-axis image, then you can do stereo. So there's hundreds of stereo pairs now. They tilted the whole spacecraft because it wasn't on a gimbal. But they tilted the spacecraft and have been imaging off-axis and being able to do high-resolution stereo. And zooming in on just the bottom part here, this is sort of the resolution. So these are individual sand dunes, and you have this meter-scale vertical resolution and 1/4 meter horizontal resolution of the surface of Mars. Here's that delta I was showing. So I'll zoom in on a middle piece here. So you can see where the water flowed here, it went around that bend, and then eventually it got cut off by this meander, then flowed a different direction. And these are the channel floors that are now the high places, because they're the coarser sediment, and the finer sediments around them, over time the wind has blown and eroded away the fine stuff, leaving the channels as highs in this case. So, and then finally the recent rovers and what they've been doing. So these are the ones that went in 2003, about a meter high mast, have a stereo camera up there on the mast, and then out on the arm here had a microscopic imager that can give you sort of 150 micron resolution. But again, you have to put the arm right up to a rock. So you're getting sort of the local context and also the fine scale texture. So first image was not very good, but start to see the local geology there. So this is sand dunes at the Meridiani site, some bedrock poking up there. They found a number of meteorites, over a dozen meteorites. No, this is not true color. Yeah, so unless you're getting a red atmosphere. So these are color enhanced to show off the differences in geology. And yeah, I'm not sure which bands they're using. They have a nice set they like to use. Sedimentary rocks with all sorts of interesting salts within them. So this is the edge of a crater here. This is about where that view from above was. It took it. Then the other rover investigated this potential small little volcano here, the circular deposit. This is the track of the rover as it went around and made its measurements. But saw evidence of volcanism, and then it had a wheel that broke, so the wheel wouldn't turn anymore. It has 6, so it can still drive. It was just dragging that wheel along, and it dug a trench for the last half of the mission, and it dug up all this interesting stuff. Like, whoa, that's different. So they took a picture behind and then went back and measured this, and it's all sorts of sulfate salts that are, you don't see on the surface, they're just under the surface. So maybe it was good that the wheel broke eventually. And then the one that just went, Curiosity, launched in day after Thanksgiving, 2011, and got there about a year later. And this one planned at least full 2 Earth years of observations and 20 kilometers of driving is mission success for this. So yeah, to compare the little one and then the ones that went, and now we're up to this one. And you'll note that these have solar panels, and this one does not. It has plutonium in the back there that is just slowly decaying. That heat there converting to electricity and powering the rover. But this mast is 2 meters high. So this is a big rover. This was about 1,000 kilograms, and a lot of challenges to land that thing on Mars. And a whole bunch of good instruments. So you have nuclear power, so your power is not a big issue. You can run lots of instruments, and so a lot of cameras, both the context and a microscopic imager that's out on the arm here. A bunch of spectrometers on board, looking at bulk chemistry of the rocks and also quantitative mineralogy. This is a neutron detector that's looking at hydrogen in the shallow subsurface and any water, either free water or bound in minerals. Radiation detectors, we don't really know what the radiation environment is at the surface of Mars. So, we should probably measure that before there's some people there and they all die of cancer in a month.
Are you detecting neutrons from the rover that bounce off the water down below?
This is a passive detector. So cosmic rays will generate various types of neutrons, from thermal to epithermal, fast neutrons. And by measuring the difference of those coming out of the surface, then you can back out. So hydrogen is a really good scatter of these. And no, they could. Yeah, and of course any radioactivity, they might measure something out of that too. But yeah, just to show you the size of this as it is being built, very, very complicated rover. And the imager is there. You have this mass cam, that's again 2 meters high, stereo cameras, 2 identical, pretty good focal range there, zoom telephoto, 14 different color wavelengths into the near infrared, but mostly just visible. Yeah?
So why so many stereo cameras? Is it for redundancy or is it for doing like 3D?
It's mainly the 3D, right? So for one, yeah, navigation, we need to know how far away all the rocks are. But planning science, we want to know where to drive this thing to maximize the science along the path.
Doing all the signal processing there and then sending it back.
Yeah. Yep. And yeah, these are coming back compressed. And then out on the arm has a hand lens, so looking at, getting you, about 20 micron resolution. If you put the instrument on a rock, you can resolve features at that sort of scale. So and this is really useful for geologists because looking at the actual grains and textures tells you a lot about how those rocks were emplaced and what processes happened there. So from the stereo camera, here's another false color shot of it, where it is right now in Gale Crater. So the goal is to go and explore these large layered terrains there. And this mountain's about 5 kilometers high. And the hope is to drive all the way up it. And you can see distinct differences where the dots are there. You can see these layers are all horizontal, and then you have layers that cross-cut them, so these erosional unconformities. So the thought is to sort of look at the time history of the climates and water-related processes occurring on Mars by climbing up this mound. And just like, you can look at the lower rocks and the upper rocks and resolve what was happening on the Earth in the Grand Canyon. So yeah, this is where the rover is. It's actually down in this stuff now. And like I said, I just went into safe mode, but hopefully it'll be back shortly and then try to figure out a way to drive up this mound of stuff. And then I've already found some interesting stuff. This was an old stream channel here on Mars. So these rocks, you can see they're very rounded pebbles that are eroding out. Here's a similar stream channel on Earth of where these rocks are in place there. So you're already starting to figure out some of the hydrology and the surface water and its character when it was flowing 3.5 billion years ago there. And then the microscopic imager, this is a recent image from it. So this whole thing is only 3 centimeters across. And so we're getting pretty good resolution looking at the surface there. Here they were testing the drill. And they have a drill that's going to drill down, or has recently drilled down into the rocks to do chemistry and mineralogy. So this was testing the drill and seeing how much force they needed to apply to drill into these rocks. But you're doing pretty good imaging here. And I'll note though, you can see this stuff's all out of focus and this stuff is sharp. So you do have pretty narrow depth of focus in these instruments. Took a self-portrait, had the camera out on the arm that pointed back and took a bunch of pictures, and then they moved the arm so they could get it out of the image. But here's the self-portrait of the rover there on the surface of Mars. So then,
You mean the camera will be detached from the Earth?
No, they moved the arm out of the way. So out on this arm is where that microscopic imager was taking pictures back, and by moving it enough, they were able to cut out the arm from it. Yeah, yep. There's no other camera looking at it, so it's your only self-portrait you can get.
You're trying to create more conspiracy.
Yeah, where's it attach? Out the front here is where it attaches. So then finish very quickly. Traditional imagers, right, have a lot of issues, and only part of it's in focus. You have shadowed regions. You can't see into. You can only use them in the daytime unless you have light sources. So you have to get the rover in exactly the right spot to be at the right depth of focus to actually get good images. So I've been working with Dan and Kelvin here. They've developed this structured light imaging module that I won't go into really any details, but there's 2 separate cameras, or imaging systems more properly, that is looking at wide scale field of view, and then also remote microscopy at a distance. And they're proven to me that they can get sort of this micron resolution at meters away with this technologies. And you know, otherwise you have to drive the rover up, turn the arm, put the arm on it, take the picture, and here you could do it remotely. Just look around and collect the same data. And very low weight, low power, low complexity, right? So I won't even go into this because I'm over time, but there's how they do it. Here's Dan set it up out in his yard and taking pictures of rocks. So again, from this 5-meter distance, you're getting very fine resolution of these features by illuminating it with structured light, and then pulling that information back and creating it into a 3D image. So like I said, this has advantages over traditional. You're seeing a very good resolution at distance. Since you're illuminating the scene, you can do day or night. You can do in the ultraviolet, any sort of wavelengths you want to use. Very rapid. So this would be good for driving the rover. A very quick collection of the 3D point cloud in front of you. Don't have to move the rover that much, and doesn't take a lot of power or mass, which are big constraints on a spacecraft. So there's a mission going to Mars in 2020. That'll be a copy of this rover, the baseline design. So we're proposing this instrument to send to Mars in 2020. So we'll see how that goes. But just in overall summary, really understanding anything about Mars, it's taken imagers. We've learned so much about geology, the history of water, what the climate must have been like, the chemistry, mineralogy, the surface physics that goes on Mars, and really through time and imaging systems. And you know, you saw this grainy black and white Mariner data up to these high resolution DEMs that we have now. It's just been a huge jump in our technologies, and that's really enabled an enormous increase in science. So we continue to just learn more and more, and of course this brings up more questions. And really, it seems like it meets the requirements for life. Certainly in the past, when all this water was around, and even at present, I showed you the evidence of these shallow bodies of water there, modern day Mars. So if we're looking for life beyond our own planet, I'd say Mars is a pretty good spot to look, and this is why NASA's really been working so hard to explore it and understand our close neighbor here. So I'll end there and take any other questions you have. Thanks. Calvin.
So it seems like the resolution of these images is even better than what we get on Google Earth. How many of the images have actually been looked at by people? And how many of them are just bits in a computer that have never been looked at?
So everyone that comes down is looked at quickly by someone, right? And they're like, this is interesting, let's put in that pile for a further look, or, oh, okay, it just goes over there into the archive. And yeah, out of quarters of millions of instruments over a few years from a lot of undergrads and grad students got hired to, you just look at every image that's coming down and tell us if there's exciting stuff in there or not. And certainly there's a lot of good science still hidden in those. Yeah.
Are those images available for the public to see in any way?
Yeah. So every image I showed is available. NASA archives all their data within 6 months of acquisition. So after 6 months, it'll be on their website, and you can go in and get it. And if you want to look at a certain place on Mars or with a certain instrument, you can see what data are available. They have good search tools for that. But yeah, it's all there because it's taxpayer money, so they get it out to everyone to have and to hold. Yeah.
Yeah, so how long ago do people know how long ago Mars was watery? Big water away?
Yeah, that's a whole separate talk or two. But I do a lot of work on the river valleys and when those form, how long they take to form. It seems like they take millions of years to form, some of those bigger ones. They're the size of the Mississippi River. And just to carve that thing and move that much sediment out takes millions of years. It seems like by at least 3.8, 3.9 billion years ago, there was a lot of water around. And billion. So 4.5 billion-year-old planet. by 3.8, there was a lot of water. It lasted maybe 300 or 400 million years. And then seems to have turned to this cold, dry state ever since. And yeah, so how do you go from a 2-bar atmosphere to 0.005 bar atmosphere? Well, Mars had a magnetic field early on. So it had a dynamo that was driving a magnetic field, helping shield the atmosphere. But smaller planet, the core cooled off quicker, no longer had convection. You lose the dynamo, lose the magnetic field, and then just solar wind will strip away the atmosphere. So we think probably 90% of the water that was at Mars originally has been lost to space. And big impacts will degrade an atmosphere too. Those volcanoes, certainly as early of records as we have, 4 billion years ago, there was volcanism everywhere. And the youngest lava flows on Mars that we can reliably date is maybe 5 million years, 10 million years. So from 4 billion up until almost now, certainly there's heat sources in the subsurface. Just there's nothing erupting right now, but things will probably erupt again. Not in our lifetime, but the next million years, probably some lava flows on Mars. Yeah.
There is kind of a process of the privatization of the space exploration.
Yes. Do I see any what?
Private company taking the lead to send something to Mars.
Yeah. So I mean, Mars is a lot tougher than the Moon or low Earth orbit because it's a much longer journey, a lot more difficulties there. But there's one group called Mars One. So you can Google Mars One, and they're designing a reality TV show to raise money to send people to Mars. So like you select, whether you love them or hate them, I don't know which ones get sent to Mars. But in 8 years, they hope to send people to Mars. I don't think it's gonna fly, but so to speak. And then just this past week, the Daily Camera had an article. Some billionaire wants to send a married couple to Mars in 6 years from now for just $1 billion, which is half the price of this rover. So, but it would just fly by Mars and then come back, so it wouldn't land on the surface. But first people to honeymoon going past Mars there, and that's a good test of a marriage, a 3-year trip to Mars in a little spacecraft.
So the atmosphere is a lot thinner than here, about a factor of 100 or more.
Yep.
What's the typical orbital altitudes that are achieved in satellites, and how low could you potentially orbit and maintain an orbit for years?
Yeah, these are typically 250 to 400 kilometers up. And the one that's launching this fall, it's going to do more of this sort of elliptical because it's an atmospheric mission, so it wants to profile through the atmosphere on each pass. And I think their low passes come down to 60 kilometers from the surface. Yeah, but yeah, which is amazing. Out there at Mars, you can have that good engineering to get you there. But on that one, there's no cameras. So even though you could get really good images, it's looking at escape off the top of the atmosphere of Mars and where the water went and by what various processes. So it's a lot more space physics.
Has anybody ever probed into the soil using the radiothermal techniques? Essentially radio waves.
No, those are proposed. So ground penetrating radars have from orbiters. We have sounding radars that have looked into the subsurface. So we've mapped out where the base of the ice caps are because you have a good dielectric constant between the ice and the ground. So those we've seen, but on a rover, no. And there's good concepts developed. They've tested them around the world. It takes a fair bit of power and mass. And yeah, then you have to interpret without any ground truth below you what those reflections actually are.
Okay, let's thank you.
All right, thank you.